Good evening guys, welcome to our new video. So today we are going to learn about how to set up the case in Converge version 3.0. So the reason we are coming up with this video is basically there are few changes while setting up the case in Converge version 3.2 as compared to Converge version 2.3. Right, all the videos which you will be watching in the future class has been recorded in Converge version 2.3. So don't worry about anything, right, because most of the things are very much same. Few things is different, which I'm going to cover in this particular video, so that you will not face those issues while setting up the case in future. Okay, so let's get started with the first challenge which we'll be working on, which is nothing but a flow through channel, right, which is nothing but a rectangular duct. And make sure you are watching this video and also the video which is recorded in version 2.3, because a lot of things will be covered in that video which will not be covered in this video, because here my main focus will be only to cover the differences or the changes which you will encounter while setting up the case in version 3.0, and that is where my focus will be in this particular video, right? So I will just walk through the entire setup for you, but I will not go much in detail because that is already covered in the further classes, which is the only thing is it is recorded in version 2.3. So the first thing is you will be creating the geometry as shown in the further class. So how to create a geometry and all those stuff will be already shown in the further class, so don't worry about it, that how to create the geometry, how to flag the boundaries, and mostly you will get confused with the terms which I am using here, but not to worry about it, right? So basically you will be creating the geometry in Converge Studio, you will flagging the boundaries, right, and then you will be setting up the case, which I have already done here. If you can see on the extreme right hand side, there is a case setup tree. So this is basically known as case setup tree, okay, on the extreme right hand side. If you can see here this thing, if I am moving this, right, this is known as case setup tree. Now first thing what you have while setting up the case is you have to click on application type. You will get the options. So in 2.3 there were options like 3 options, which is steady state, transient state, and crank based. So now here it's like time based, crank based, crank angle based IC engines, crank angle based non IC engines, example pumps. So you have to click on time based, and then you have to click on apply and done. Okay, and then you have to come here in the gas simulation, nothing to touch, you have to just click OK. Global transport parameters, nothing to touch again, click OK. Species, exactly, so here you have to select the species. Okay, so you have selected air as the participating fluid, so air is nothing but O2 and N2, so you have to select O2 and N2 from the query available list, right? And then you have to click on OK. And then in the simulation time parameters, once you click on run parameters, here is the thing. So now the first simulation which will be running for the channel flow will be the steady state simulation. Okay, so there are two types of simulations. One is steady state and another is transient state. So both are time based, right? How is time based means, if you are running steady state simulation, the time will be in terms of cycles, and when you are running transient state simulation, the time will be in terms of seconds. And when you are running crank angle based simulation, time will be in terms of crank angles, correct? So if once you click on the solver drop down menu, you will get transient or steady state solver. So you will click on steady state solver because you want to run steady state simulation. Now here in the simulation mode, there will be two options, full hydrodynamic and no hydrodynamic. So it's very simple. I will just explain these terms in a very brief way. So no hydrodynamic solver is nothing but whenever there is a complicated geometry and parts are moving and rotating, you will first always run no hydrodynamic. And why you will run no hydrodynamic is when you are running no hydrodynamic simulation, it will only generate mesh. Okay, it will not solve any hydrodynamic equations, that is, it will not solve Navier-Stokes equation. So Navier-Stokes equation is nothing but a combination of momentum equation, energy equation, correct, and the continuity equation. So it will not solve any of these equation and it will only generate mesh. And it is if you are running no hydrodynamic simulation, it will take very less time. aim is just to create mesh and nothing else. And why you have to run no hydrodynamic first in the complicated geometries where the valves are, let's say if you take an example of IC engines, so valves will be translating, piston will be translating, correct? There will be geometries in which things will be rotating, like compressors and all those things, correct? Impeller wheel will be rotating. So in those cases, it is always a good idea to generate the mesh first. Why? Because while generating the mesh, if there is some problem, let's say you flag the boundaries incorrectly, and because of that the mesh is getting stretched or it is getting overstretched, and because of which intersections is happening, or there are some parts which is intersecting with the other walls, right? So what will happen is when such cases are when such incidents are happening, basically it is leading to case crashing, right? So to avoid all these things, let's say if you directly run full hydrodynamic for such cases, what will happen? It is going to be very time consuming, right? Because it is going to solve each and every equation in each and every cell. And let's say after running 1 second, right, some part is intersecting with the another part, and now you have to rectify that. So let's say that 1 second took around, let's say 2 days, right? Then that 2 days you understood about the problem after 2 days, and now you will be working on those issues, and then you will be submitting your case again. So that is not an ideal way to run, right? Because obviously energy is wasted, electricity is wasted, time is wasted, which is not a good point from an engineering point of view. So let's say if you're coming to know about any problem in your geometry or in your simulation in an hour or 45 minutes, why to spend 3 days to understand that problem, correct? So always you have to run no hydrodynamic in case of complicated geometries where things are moving in the sense things can be translating, rotating, correct? Now in the channel flow case, it's a very simple geometry. There is nothing, no parts are moving, right? So always go with full hydrodynamic, correct? Geometry is simple, very straightforward. You can directly go with full hydrodynamic. And gas flow solver, compressible. And then what you have to do is you have to go in miscellaneous. Okay, now this tab you have to go on in the miscellaneous. So besides solver, I think you will not be able to see my mouse pointer here. So what I'll do is I'll just keep on taking the names in which I'm entering. So first one is the solver, in which I explained about all these things, and next to the solver tab there is a miscellaneous tab. If I click on this, you will get to see all these things. So here you don't have to change anything, except you have to check the box of steady state monitor, and you have to uncheck the used shared memory. Okay, so it will be by default selected like this, but you have to uncheck this. So what is the meaning of use shared memory, right? So in previous version of 2.3, what was happening was geometry is really big and complicated. Geometry itself will get distributed among the different processes, the surface triangle, the properties. So those information will be distributed among the processes. Again, nothing to worry about this concept as of now. Just remember that you have to uncheck this checkbox of use shared memory, and you have to check this box of steady state monitor. I will explain you this point about steady state monitor. So now you have to just click on OK. Now once you click on that steady state monitor, you will be able to see this parameter steady state monitor here in the under your case setup tree. So when you click on this case setup tree, you will get a window like this. Okay, so now what you have to do is basically here you will not be able to see anything. So let's say I will just okay, I will just delete this for your reference, right? Okay, yeah, so now you will be able to see like this. So now this is very important. Okay, what is the meaning of steady state monitor basically? So what this particular option means is, if you are running steady state or transient state, doesn't matter. At the end of the day, you are basically looking for some of the quantities to be converged. Let's say you are interested in knowing that at the outlet the velocity should get, you are interested in knowing the value of the velocity. At the end of the simulation, you are interested in knowing that what will be the pressure at the outlet, right? Or if you're doing any HVAC problem, you will be interested in knowing that at the end of the simulation, what will be the temperature of the room, correct? So in any case, your ultimate goal is basically to monitor some, not monitor, ultimate aim is to get some values out of the simulation. So if you're very much confident about the output results that you want to see these results at the end of the simulation, what you can do is you can monitor those variables. Meaning, when you, let's say you want a pressure, velocity and temperature to be monitored, then you will add those values here, click on add 3 variables, and monitor variables you will select from this thing. Let's say you want to select average temperature, you want to select total pressure, then you want to select let's say density. Okay, I'm just randomly taking it as of now, and the target type, correct? So what is the target? So you want to obviously check those things at the boundaries. So boundary, but now which boundary, correct? So you have to select from here, inlet or outlet. So since here they only so whether you have to check what is the average temperature of the fluid coming out of the geometry fluid domain, or what is the average density right at the outlet. So what you do, outlet, and outlet. Depends upon case to case where you want to calculate what. Okay, and all these things are very detailed, and you will definitely be learning in further classes. So I'm not diving deep into all these concepts as of now. My main aim is to show you how to set up the case in Converge version 3.0. So these are all the different things which you will not see in 2.3 version. It means you will not see in the video, because video has been recorded in 2.3, right? So that's why I am coming up with this new video, so that I can show you that these things you will be encountering and how to deal with. So let's say you and you're running any simulation and you are interested in knowing the values of these 3 things at the end of the simulation at the outlet. So you define this. Now this you can so you can select that from in where you will be basically getting all this. So it will be basically dumped into mass average flow dot out. Okay, so now what it will do, so let's say your in time of the simulation is 15,000 cycle. Okay, and all these quantities are getting converged at 7,000 cycle. So the advantage is the solver will not care what is the end time you gave for the simulation. If the variables which you are monitoring is getting converged within 7,000 cycles, your simulation will normally terminate, meaning it will stop the simulation and you can post process the results and look at the results. Simulation will be done. So let's say for 15,000 cycle it has to run for 3 hours. So definitely for 7,000 or 8,000 cycle it has to run for 1.5 to 2 hours, correct? So you are saving a time, right? So that's why it is said that in Converge 3.0 simulation runs faster because of this particular option they have incorporated, right? And it makes a lot of sense, right? Because in steady state your main aim is not to see how the temperature or pressure is changing with respect to time, but rather your ultimate goal is that what is the end result. Let's say what is the average density or average temperature at the outlet for the fluid, correct? So basically you have to monitor that, and if you're monitoring that and once those quantities are converged, like after 7,000 cycles, the values for these particular variables are not going to change anymore, then why to run the simulation for another 7,000 or 8,000 cycles? It doesn't make any sense, right? So that's why this is very useful. Now let's discuss about some of the parameters here. So the first parameter is like minimum number of cycles to be executed for the steady state solver at the very top. So this is like when you want solver to start monitoring the variables which you have listed below. So here it is mentioned 5,000. So you are telling to the solver that after 5,000 cycles, right, start monitoring these values. So minimum number of cycles that your simulation will undergo is definitely 5000. It can't stop before 5000 because you are mentioning here, right, 5000. Let's say if I'm mentioning here 500, so minimum number of the cycles will be this much. Now let's say if I'm keeping 1000, let's say 500 here, that minimum number of cycles to be executed for the steady state solver to be 500. So till 500 it will not monitor these variables, but after 500 it will start monitoring these variables. And let's say at 1000 cycle all these variables are converging. Then at 1000 cycle your simulation will stop. It doesn't matter whether what's your end time. If your end time is 15,000 also, then also your simulation will normally terminate, and because the variables which you are looking for at the end of the simulation has already converged, so you already got the results, then why to run for more, right? It makes sense. Now let's say in the same scenario you are keeping minimum cycles to be 5000, right? Then you know that at 1000 your simulation is all the variables are converging, but before running the simulation no one knows, right? So let's say you kept here 5000, then it will run till 5000 because you have said to the solver that minimum number of cycles to be executed for the steady state solver should be 5000. So after 5000 it will check and then it will stop. Even though the variables which you are monitoring has converged at 1000 cycles, it will not stop because you have kept here 5000. So you can play with this number accordingly. Let's say if you want to run till end time, like that is 15,000, so you can directly type here 15,000. That's it. No matter if it is if your monitor variables are getting converged at 1000 or 5000 cycle, it will run till 15,000 cycles. That is how it is, very straightforward, right? So, and then here monitor units, obviously you are running steady state simulations of cycles, you have to select cycles. And if you are running transient state, and if you want to monitor some variables, and you will click on seconds, right? But this is steady state, so I will select cycles. So here monitor start delay, right? So from which cycle you want to basically start to monitor. So since here you have already told that okay, after 5000 you have to, like, minimum number of cycle will be 5000. So now here is the thing. So when you say that monitor start delay in cycles, so after 5000 cycles, here is the thing. Now it might be little bit confusing, but it is not. So here what I said, that it will run till this much minimum number of cycles. But now let's say if you are selecting here 0 cycle, that means you are telling the solver to monitor these values from start, but don't terminate the simulation even if these variables are getting converged before 5000 cycles, right? So minimum it will run for 5000, and let's say if you're saying at 0, from the 0 cycle, mean from the start of the simulation start to monitor these variables, that's fine. And if you wish that okay, anyways at the start of any simulation everything is unsteady, correct? So it doesn't make sense to start to monitor these variables from the start, but that will not make much difference from the result point of view. Definitely it is not going to give any difference, but it's like if you're an engineer, you will be obviously doing a smart guesswork, correct? So it's like monitor start delay. So it doesn't make sense for an engineer to start monitoring these variables at the start, because he knows whether any case you take, it will be unsteady initially for some time, and after some time it will start to reach steady state, correct? So you can keep 0 also, and if you keep, like, let's say after 500 cycles start monitoring, you can do like that, or after 100 cycle or after 10 cycles, whatever you want, correct? If you want to keep it 0, that's fine. Now sample size. So what is sample sizes? Like after 5000 cycle it is reaching, basically what it will do, let's say if you are mentioning here 1000, okay, so after 5000 cycle, since you are, let's say you are monitoring from 0th cycle, that is from start, now basically it will take, after 1000 cycles, it will take an average of all the values in those 1000 cycles, and it will see whether the values which I got, let's say for this 1000 cycles, let's say there are two sets of 1000 cycles. So you are running for 15,000 cycles. So let's say first 1000 cycle and second 1000 cycles. So in the first 1000 cycle, let's say you got a value, average value of all those 1000 cycles to be 2. And in the next 1000 cycles, you are getting a value to be 2.05. So now between first 1000 cycle and next 1000 cycle, there is a difference of 0.05. Correct? So now this difference, right? So what it will tell you basically, this will be a tolerance. So we are basically tolerance type, we are selecting relative tolerance, and when your tolerance, like when the value, right, of this sample size is within the tolerance limit, the solver will understand that okay, now solution is converged and it's time to stop the simulation. But it will stop the simulation only after it has crossed the minimum number of cycles to be executed, right? So let's say if the tolerance with the values coming is within the tolerance at the 1000 cycle, then it will not terminate, because you have told to the Converge solvers that minimum number should be 5000, right? It should minimum, it should run 5000 cycle. After that only, if the value is within tolerance limit, you have to stop the simulation. So now to just conclude everything, basically there is a tolerance limit which is by default 0.01, and you don't have to touch, and also the tolerance type should be relative, you should not be touching that. Sample size, whatever the sample size you will choose, it will basically take an average of all the values for those 1000 cycles, or if you are selecting 500, then 500 cycles, and it will compare that average value with the average value of the previous 1000 cycles. Correct? And if that value is within the tolerance limit, it will understand that okay, now solution has converged. And then if it has crossed the minimum number of cycles, it will normally terminate your simulation. Otherwise, it will keep on going until the value which a solver is calculating for those sample size is not within the tolerance limit. Correct? So basically this is the basic meaning of what all these parameters you are looking here, and you just have to fill up the minimum number of cycles to be executed, and you can play with this number, because let's say you want to see till the end of the time, so you just put the end time here. So no matter whether it has converged or not converged, it will run till 15,000 like that until the end time. But it is not a smart way to run any simulation, right? So since Converge has provided us this extremely strong feature which will definitely going to reduce the computational time, then as an engineer you should not be wasting the energy, and the energy in the sense the computational energy, and also definitely the time. Correct? So basically you have to always try to optimize the things, right? So this is what I think from this point of view, and these things will not be seen in the videos which will be coming in the further classes, because that videos has been recorded in 2.3. correct? So that's why I'm covering these things here. So make sure you go through this video very nicely, make notes, and whenever in the future class if you are facing any issues related to setting up the steady state or transient state simulation, just come to this video, have a look, and then again go back to the video, and mostly you will get the solution for the problem which you are facing. But if you are doing this challenge very honestly and very with full dedication and understanding the things properly, then mostly you will not get confused, and definitely you will set up the simulation very smoothly. Correct? So this is one thing. I think there is no changes in this. When you will go through the video, further videos of channel flow, this has been covered there. Solver parameters, nothing to touch here. Yeah, one thing here you have to notice is in the 2.3 version of Converge, there was a separate when you click on that, option, you will be getting an option directly in the first window saying you want to which type of simulation you want to run, steady state or pressure based. Okay, so you will be getting those things here in the run parameters. So in the run parameters, when you are selecting this, there was one option of simulation type. Okay, so in the simulation type you have to select pressure based or density based, but you are not able to see it here because it has been shifted under the solver parameters. So under the solver parameters, if you are running steady state, there will be two options. Steady state, there will be two options. That is, you want to basically solve the equations like using density based solver or pressure based solver. So I would highly recommend to always go with density based solver, and which you will be seeing at the extreme top right corner, Navier-Stokes solver type, right? So here you can see pressure based or density based. So always go with density based. Okay, and nothing to change here. Two things here you have to take care is, like, when you go to equations here and the equation tab, so in the pressure, make sure that this preconditioner is set to none. Okay, if you don't select this to none, what will happen is when you start running a simulation, it will throw an error saying invalid preconditioners are selected. So always the preconditioner should set to none. And I think for rest other things it is all by default selected to none, but only for pressure equation it is selected to, by default it is selected to SOR. So you just click on this drop down menu and select none. This one changes there. And another thing is, in this, when you are running a steady state solver, when you click on the steady state solver control, maximum convection CFL limit, the second last option, right? The last is minimum AMR application. You don't have to see that. Above that, there is a maximum convection CFL limit final stage. Can you see this? So this number should be less than 1. You just keep 0.5. Okay, what is this, how it works, you will come to know in the future classes. This is too early to understand these concepts, but whenever you are setting up the case, make sure that this is less than 1.5. okay. If you don't keep it less than 1, you will be getting an error saying that steady state convection CFL limit is greater than, if you go to simulation time parameter, and maximum convection CFL limit. So this is 1. So that steady state CFL number should be less than 1. Okay, don't get confused. Again, this is not the motto of this video. Just for the completeness, I just showed you. So to conclude for this window, there is the option of pressure based and density based here. Always go with density based. In the equations tab, you have to go and go to pressure equation and make sure the preconditioner is set to none. It will be by default set to SOR. Make sure it is set to none. And you can just cross check for all the other equations. It is already, the preconditioners are set to none. But wall distance, I think that is not going to cause any problems here. Okay, so don't worry about it, because that is something related to the turbulence modeling. And when you are using a particular turbulence model like K omega SST, at that time this thing will come into the picture. So here you are basically not using the turbulence model, and in the further classes, whenever you will be using the turbulence model, in fact in the IC engine course, you will always be using the RNG K epsilon, so you don't have to worry about wall dist, but you only have to consider about pressure. So make sure that in the pressure equation, preconditioner is set to none, and then you have to come to steady state solver control. In that, your maximum convection CFL limit final stage, which is the second last option, that should be set to 0.5 or any number less than 1. Then click on validate. Okay.